Welcome, thank you for coming. I'm Olson, I'm the chair of the OpenGL ES working group, and in the spare time I work on. We've got, well, we'll get to the agenda in a minute. This is, as you know, a big year, most of you know, for the OpenGL ES working group. We have a new standard to announce. Most of what we're going to talk about today is that stuff. So I'm going to do just a minute or two of beard stroking and remembering how we got where we are. Then I'm going to turn the floor over to Benj, who is our specification author for the new API. He will walk you through technically what's in it. Bill, I see a Kane, will perform the same service for us for the language. I see Bill, I don't see Benj. Hopefully he's not too far away. I'll do a little bit of wrap up and talk about a few things not related to the new API. And then we'll close with a sort of jack-in-the-box series of, we have a number of people who have, related products or news that have something to do with GLES3, and we want to give them a chance to present a little bit, show a little video, etc. And I'm going to try to keep an eye on the time. So a little beard stroking. The last day of Siggraph 10 years ago, a bunch of us met around a coffee table in Neil Trevitt's hotel room, high up in some building somewhere. It was probably here. And agreed that we were going to try to work together to develop a mobile version of OpenGL that we could all agree on. At the time, there were dozens of them, all different. And the industry was in a kind of a shambles. By working together, we were able to do that. We got it done in 1 year. Released our first version in 2003. Realized we'd missed the duck a little bit, hadn't led far enough, so we released another version in 2004. Started immediately working on shaders, and it took us more time. It took us 3 years to do that. In the meantime, something else was interesting was happening. After ES2 came out, and we had immediately, of course, started working on ES3, it was only then that we began to get hardware platforms that people could, independent software people could write software for and sell it in the form of the iPhone and the early Android devices. And they were all running ES 1.1. So our new standard was out, but all the market momentum was toward 1.1. So we worked on 3.0. In the meantime, 2.0 devices came out eventually in 2009 and 10. But the market was very fragile, and we thought, man, if we release a new spec now, it's going to drive everybody nuts. Let's stop working on 2.0. We don't want that. So we kind of sat up on our hands for a little while, polished the spec, worked on conformance, and held back. Last year was the exciting year for me when we began to see really first-class AAA games and game engines beginning to appear on ES2, and we decided now it's time. Hence, OpenGL ES3. Now, if you are good at recurrence relations, you think 1 year for the first, 1 year for the second, 3 years for the third, 5 years for the fourth, I can solve that. That predicts that our next standard will be out in 2021. But that's actually not the case. It is likely to be less than 5 years. I don't want to make promises. But the market is moving now. We have content flowing through the pipe. The circuit is closed. And so we think things are going to happen relatively fast from now on. A little bit of what I started with when we began working on 3.0, there were a couple of things that I wanted, and I think all of us in the working group wanted. First and foremost, to expose the appropriate feature set for the next generation mobile device, obviously. But also, so that was the obvious one. Maybe less obvious, we recognized that 2.0 posed some problems for developers. There was a lot of variability between implementations. The spec allowed it. The spec was kind of loose in terms of what must be there versus what can be there. We wanted to fix that, have a better defined, tighter set of requirements for what conformant implementation is. Also, because of the time we were working, we didn't want to demolish the economic momentum building behind ES2. And for that reason, we committed very early to making it backward compatible. So no compatibility break this time. Next time, all bets are off. But that's where we are. At this point, I'd like to turn it over to Benj, hard-working specification author for the last 5 years on this project, who will tell you what the API is.
Hi, I'm Benj. Last time I was up on this stage was 4 years ago when we were announcing the OpenGL ES 2.0 man pages. And I'm happy to be back talking about OpenGL ES 3 now. I could probably just leave this slide up for the next 25 minutes and you can kind of get a feel for what features are in this spec. Instead, I'll try to race through them in 25 minutes. This is the biggest new release of OpenGL in the history of OpenGL, really, the last 20 years. It helps that we don't release specs more often than every 4 years or so. So it gives us an unfair advantage. But this is 50 new features, more than 50 going into ES3. And just to give you a little bit of context, you can see that ES3 is a superset of ES2, like Tom mentioned. I'll talk a little bit more about that. But you can also see it in the context of desktop GL. ES3 is derived largely from OpenGL 3.3, although we also borrowed some stuff from more recent 4.x specs. Now the story behind ES2 code on ES3 is that it just works. However, there are a few caveats. They're just minor changes of behavior you can expect running your ES2 code on ES3. First is that in ES3, frame buffer objects, which are considered container objects, are not shareable across contexts. In ES2, it was a little ambiguous. Some implementations did share them, some didn't. It's undefined in that spec, but we've nailed that one down in ES3, so expect the sharing not to happen. Cube maps. In ES2, the way they are defined was that you are always just picking one face of the cube and then doing all of your filtering there. So if you're fetching from the corner of a cube map, either you're going to clamp to that corner or you may wrap to other corners. But what you really want to have happen is to involve the neighboring faces. And that's how we mandate things in ES3. The last subtle change is in the mapping between floating point numbers and signed normalized fixed point numbers. So if you're dealing with 8-bit quantities, in ES2 they used to map -128 would map to -1, +127 would map to +1, 0 didn't quite map to 0. And so that's something that we fixed. Now -127 maps to -1, +127 to 1, 0 is dead on 0, and -128 is also -1. So that's the new formula we have. Everything else should be the same. Except we've also raised the bar on minimum maxima. So these are the limits that every implementation is required to support. At least this big of a texture, at least this many texture units. So an application doesn't need to query the limit if it knows it's going to use only up to these limits. You might get all nostalgic when you see that the limit in ES2 that implementation is required, for example, for cube maps, 16 by 16, that's kind of cute. And render buffer size only need to be 1 by 1. So enjoy your 2K size dimensions. But the real thing to take away from this slide is you notice that vertex texture units used to only require 0, now we require 16. Plus 16 on the fragment side for a total of 32, so that's a big improvement. Now, we've got so many new features. I've tried to categorize them in a useful way. So I'm going to be talking about the new formats in ES3, the new texture enhancements. I'll talk about features that are aiming at efficiency and synchronization. But that left a few extras that are kind of in this junk drawer slide. The first is kind of a headline feature for ES3, and that's transform feedback. And so that allows you to stream out the vertex shader outputs to a buffer object. You can optionally continue to rasterize the data and then go on towards the fragment side of the pipeline. Or you can just feed them into this buffer object, which you'll usually want to recycle that buffer object either as a uniform buffer or as a vertex buffer in subsequent passes. But if you want, you can just read that data back and use it for general compute purposes. I know you've all been waiting for your 2x3 matrices. Now you have them, and you can transpose them on the way in. So enjoy that. You might not be aware that ES2 did not even require an online shader compiler. It was perfectly valid to have an implementation that only accepted shader binaries. And now we require that every ES3 implementation take source GLSL shaders in. So most of them did anyways, not a big improvement, but there you go. Program binaries. So if an implementation supports program binaries, this means that they'll be able to send in a pre-compiled vertex shader and fragment shader pair, pre-compiled, pre-linked, ready to go. The idea is to avoid the cost of running the compiler at runtime. And then those implementations will allow you to retrieve program binaries back out. So the common use case for that would be sending in GLSL source shaders the first time, compiling them and linking them online, and then retrieving the end result, storing it somewhere, and in subsequent runs of the application, feed them back in the same way, thereby avoiding some or all of the cost of compiling and linking it online. We support draw elements with 32-bit indices now. Yay. But caveat, only 24 bits are guaranteed to be valid. There's a query to let you know if you can use any of the upper 8 bits as well. And the last one in the junk drawer is a new way to query for extensions. So the old way is you get back this blob of unknown size and you have to parse out the extension strings and look for things you're interested in. Now instead you will query the number of extensions and use an indexed get string query to read each one back one at a time, which should avoid a lot of bugs where applications would reserve just 2K of space for this extension, and because who would ever have more than that many extensions, and then your app will crash a day later when someone comes out with one more extension that blows past your limit. So this should be less parsing code you need to write and less error prone in the end. Okay, lots of new formats in ES3. Drum roll for the first one. RGB8 and RGBA8. Can you believe that these were not in ES2? They were not. They were an extension. So we'll start with those and we'll move on to signed normalized versions of these, in addition to those unsigned normalized ones. sRGB. So this will be getting the most bang for your bits by storing the data in perceptual space instead of linear space. And all of these ones you see here, along with the ones that were built into ES2, that would be the packed RGB 565, 4444, 5551, all of these implementations of ES3 are required to support them at 4x MSAA at least. Moving on to additional formats, we're steering away from luminance and alpha, which we consider legacy kind of capabilities, and instead using red and red-green base format textures for our single and dual component formats. Floating point textures. So we support 16, 32-bit, a packed 111110 floating point format, and a shared exponent RGB9E5 format. All of these are filterable except the 32-bit floating points. And we add half float vertex attributes. In ES2 we had the full float. Now we're adding half float. A little more efficient. We have supports for real integers, both signed and unsigned, 8-bit, 16-bit, 32-bit, pretty much everywhere in the API. That includes textures, render buffers, and vertex attributes. And we also have a 10.10.10.2 packed format, which is used for textures and vertex attributes as well. Now we had 16-bit depth component render buffers in ES2. We've added to that 24-bit as well as a 32-bit floating point depth format. And for those 24-bit and 32-bit float versions, we have packed 8-bit stencil to go with them. And those can be used not just for render buffers, but also as textures now. I'll talk a little bit more about that. Under texture enhancements, the first one is Your format no longer needs to equal your internal format. So you have these sized internal formats, just like desktop.gl. These aren't just a hint. This is a minimum requirement. If you ask for 8-bit, you're going to get 8-bit. You're going to get at least what you ask for component resolutions. We've introduced 3D textures, as well as 2D array textures, which are a layered array of 2D images. I talked about adding depth texture support. We have shadow comparisons to go with those. So comparing the depth value in the texture against the reference depth value, common native for shadow mapping. And swizzles. So the RGBA color data that you're reading from the texture unit, you can rearrange the components, you can replicate them, you can substitute it in zeros and ones. It gives you lots of flexibility in what will eventually get delivered to the texture lookup function in GLSL. Or texture enhancements. So we had limitations on non-power 2 textures in ES2. Now you have full MIP mapping, rack modes, everything. No more caveats there. These next two, so we've got LOD clamping, which is clamping the continuous lambda calculation, deciding which MIP level to look up. Post bias, you can clamp that to a min-max value, and you can also specify an alternative. Instead of 0 always being your base level, you can specify a range of MIP levels that you want to be used. So combining these two, you can do texture streaming using the level control to load in entirely new levels as your base level, and then use the LOD clamping to kind of fade in and out between the changes in the. And now we have the ability to attach more than just the base level to an FBO, then it can be rendered to texture to an entire MIP array. That's it for texture enhancements. Now, this next group of features is all in the name of efficiency. We have instance rendering, a couple different ways of achieving that in ES3. So the idea here is you, instead of drawing 1,000 blades of grass individually with separate draw calls, because you want each one to be a little bit different, now instead you can use one draw call, and your vertex shader is going to get a GL instance ID, and you can use that for anything you want to customize that particular blade of grass. You can use it to index into an array of uniform matrices, for example. The alternative to using that GL instance ID is using vertex attribute divisors. So those let you set up your vertex attributes. So instead of each vertex attribute incrementing once per vertex, you can set it up to increment them once per n number of instances. So you can set up vertex attributes. So every 10 blades of grass, we're going to change the color or change, whatever it is you want to do. So two different ways of getting instance rendering. Primitive restart is an alternative to a hack you may be familiar with, using degenerate triangles to jump around in space between discontiguous portions of a mesh to try to fit them all into the same draw call. Now we have a first-class citizen way of doing it. You just use a max value index, and that'll signal, okay, this is the end of the last triangle strip, beginning of the next one. Draw range elements lets you tell the implementation when you're doing a draw elements call that you're only going to be using a particular range of indices, which means if you're using client-side vertex arrays, instead of having to copy out the entire set of vertex arrays, you can tell it just to copy out the portion that you're actually going to be drawing with. So if you're still using client-side vertex arrays, it's going to be, you should stop. But if you must, use draw range elements. Vertex array objects allow you to encapsulate all of the setup for your vertex attributes, the enables and pointers and whatnot, to allow the implementation to pre-bake them and efficiently switch between them. And immutable textures allow you to tell the implementation everything it needs to know up front to be able to store your textures efficiently. So instead of the old style of sending in MIP levels individually, the implementation not really knowing how many bit levels it's going to get, or whether there's conflicts in their formats, and having to do a completeness check at the end, and possibly draw black at runtime if you didn't get it perfect. Instead, all that information is baked into a text storage command, so the implementation can allocate everything up front, and then you supply via text subimage all the actual pixel data after that. A few more features for efficiency. We've got sampler objects, which encapsulate all the different sampler setup states. Again, allowing you to, implementation to pre-validate that, make it more efficient to switch between them. Also more efficient to share them across texture objects, ones that are sampler state. The most efficient way to draw something is not to draw it at all, and that's where occlusion queries come in. In ES3, we have a Boolean occlusion query, so which is the common use case. Instead of telling you how many pixels passed the depth test, we're going to tell you if any of them did, and that will allow you to send down cheap, low-res, just bounding box data, and if it comes back saying, yes, we could see a pixel in your bounding box, then you can go back in a subsequent frame and actually render the high-detail, expensive fragment shader object, or not, and that's where the efficiency would come in. Multiple render targets, we require implementations to support at least 4 in ES3. So instead of, if you have more than a vec4 worth of color data coming out of the fragment shader, instead of having to multipass to get all the data out that you need, now you're able to send colors to at least 4 different targets. This one's very important for tile-based architectures, which are pretty common in the mobile space. So when you render a scene, you're going to be probably using color buffer, maybe depth buffer, stencil buffer. You might be using multi-sampling and resolving down to a single sample color buffer. The only thing you usually care about at the end of your frame is single sample color data. That's what's going to show up on the screen. And most of the time, every other bit of that data, the depth, the stencil, the multi-sample, maybe 4x multi-sample data, it's a lot of data, and you don't care. At the beginning of the next frame, you're just going to overwrite it anyways. So this invalidate frame buffer feature allows you to tell ES, I don't care about any of that stuff, don't go out of your way to preserve it. And that's important because on tile-based renders, you switching from one tile to the next, it's going to save off all of the frame buffer data that you tell it to. If you don't tell it otherwise, it's going to save that depth, that stencil. It's going to restore all that next time it comes back to that tile. And that consumes memory bandwidth, consumes power, consumes time. So please use this hint. It's basically harmless on any implementations that aren't tile-based, and it'll save you on the ones that are. Finally, the last category is synchronization, or ways to avoid synchronization. So we have sync objects that allow us to insert fences into the command stream so that we know when certain resources we may be using are safe to touch again. So for example, if you have a vertex buffer that the commands previously inserted into the command stream may be reading or writing to, you want to update that. You can either block in the client, you can say, all right, return control to me when that thing's found its way to the bottom of the pipeline. Or you can check the status of a fence. You can say, okay, the thing's still in the pipe. Let's go off and do some more work, come back later, and check again. We've got pixel buffer objects and uniform buffer objects. So these are other ways to kind of get asynchronous behavior. For example, doing a read pixels, traditionally, you're going to have to drain out the pipeline, do the read pixels, it's going to return the data from the frame buffer to the client, and then not return control until that's done. If instead you read to a pixel buffer object, you are able to kind of make that asynchronous because it's just going to be returning it to server memory. You can march on the client side until you actually need the data, at which point, hopefully, it's already there and ready for you. You don't need to do any blocking. Buffer-to-buffer copies, both from buffer object to buffer object, as well as splitting from frame buffer memory to frame buffer memory. Because all of this memory is on the server side, you don't have to block the client can march on with its work. Finally, buffer sub-range mapping. So if you want to map a buffer object, you don't have to map the entire thing. You know that you want to update a part of the buffer object, the other half of it is in use in the pipeline. You can do that now. You get much more granular control over what you're mapping, how much work the implementation needs to do to provide you. Like you can tell it, I don't care what the data is in the buffer when I map it. You can say, give me valid data, it's fine, I'm just going to write to it. You can have control over when you flush out that data. So it basically takes the burden away from the implementation to keep your data safe for you, puts you in control, lets you shoot yourself in the foot if you do it wrong, but gives you the ability to be much more efficient. And there's just two more important features in ES3. First one is the OpenGL shading language for ES 3.0 version, and I'm going to have Bill come up and talk about that, and new texture compression formats that Jacob will come up and talk to us about in a minute. So I'd like to hand it over to Bill. But before I do, I just want to thank the ARB, because those are the shoulders that we're standing on, all of the work that they do to give us desktop OpenGL, and then we handpick the pieces of it that we want. A lot of appreciation to those guys for doing this good stuff to work with.
Hi, my name is Bill Kane. I work for AMD, and I'm going to be talking about the OpenGL ES shading language version 3.00. And yes, it is kind of amazing that the ARB does a lot of the groundwork, but I also have to flip it back around, and there are a lot of people interested in ES who are participating in the ARB, kind of helping us to move it along all the way along all of these years. So it's definitely grown into this wonderful relationship between the ARB and the ES working group. We're all learning from one another as we go along. So I'm going to start with the shader-centric view of the world, and starting with an OpenGL ES-centric view of that shader. So again, it's a functional superset of the language version 2.00. Functional superset. It's not absolutely 100% upward compatible from the shading language point of view, but you will be able to load in all your old 100 shaders with the API and with the shading language. The shader processors, the best way to think about these is they've grown dramatically more capable. You have vertex and fragment shaders again, floating point, effectively IEEE 32-bit like, integers, 32-bit signed and unsigned, and these kinds of processing powers that are out there, much more capable shader units than were there in the past. Uniform buffer objects. I know a lot of you especially wanted non-square matrices to try to be able to stuff that last couple of BOA matrices into the very limited uniform store we had in the vertices. With uniform buffer objects, 12 binding points for vertex, 12 binding points for fragment, each one of them is 16 KB, you're no longer going to have to stress about BOA matrices in the vertex fragment shader, and you really won't run out of resources on the constant store at all to be even thinking about. And coincidentally enough, these are the same limits that are there on the desktop side. Transform feedback buffers, also in the shading language, gives you that wonderful way of recirculating data through, including you could render to a vertex buffer and then mount that as a uniform buffer and be able to do the kind of update your BOA matrices and stuff with possibly a shader to do it for you. Multiple draw buffers is in the shading language. It was always in the shading language with 1.0. We actually had geofrag data, an array of it, but you only had to support one. And then, as Benj was talking about the texture samplers, many more samplers are coming in making this a much more powerful way of being able to rapidly get to mass quantities of texture data. And possibly most significantly of all, Appendix A, limitations, is gone. Not talking about removing a few of these limitations. The entire appendix from Appendix A in OpenGL ES 2.0 is gone. No more worrying about whether or not I support while loops, no more worrying about whether or not I can do kinds of branching, no more worrying about how many instructions I have to do. For all practical purposes at this point, on these devices, you're going to be running into performance considerations well before you run out of resource considerations. So that's a huge difference from just a few years ago. Now, the shader-centric view from the OpenGL-centric view. It's a subset of OpenGL 3.3. The most significant feature from 3.3 missing is geometry shaders. Now, with geometry shaders in the early days, people were trying to force fit them into doing lots of tessellation and things like that. They were a really poor match at doing that. The kind of couple of things that you can do with geometry shaders that are being done with modern apps, things like generalized point sprites and a little bit of data amplification, like turning a triangle into 3 lines, probably not significant enough to pay the penalty for the amount of area to be able to support those. So they didn't make the cut on the hardware cut for requirements in OpenGL ES, and I personally think that was a very wise choice to make. There are some cherry picks from OpenGL 4.x. Benj talked about some of them in the API side. There are also a bunch in the shader side as well. A lot of them are the category of bug fixes. A lot of them, like I said, were found by the ES group. We got put into 3.x or 4.x specs, and then the ES group took them back from us. OpenGL ES 2.0 features continue on. Examples are the precision qualifiers. Now, like I said, if you have 100 shaders, you can load in a vertex shader 100 and a fragment shader 100. Those are the ES 2.0 shaders. That was the old convention. You can use those as is, work perfectly well. What you can't do is mix and match 100 and 300 shaders. So I'll give you a very quick porting example of a simple shader. So the traditional one for the ES 2.0 one on the left side, version 100, that's implicit, the pound version 100. If you don't include it in your shader, it will be a pound version 100 shader. You have to, in the fragment shader, always declare what your precision is going to be, medium P float. You have a varying, let's say, this very simple pass-through fragment shader, varying vec4 color coming in. And then void main, GL color equals color. And that's the entirety of your simple little pass-through ES 2.0 class shader. For ES 3.0, you'll be saying pound version 300 ES. That's not optional. In order to get the 300 features, you have to declare your pound version to be that. And precision medium P float. Rather than saying varying, both ES and OpenGL desktop have changed varying from varying meaning out in the vertex shader and in the fragment shader to be explicit. I'm going to want to take this in the fragment shader. So I'm going to change my varying to in vec4 color. And ES and desktop both deprecated the built-in outputs of the fragment shader. So you're going to say with the layout qualifier, telling it to be location equals 0, essentially the first bonding point in your multiple render targets, that you want to have it out of a vec4 of data. And then your void main data equals color. And that's the entirety of a porting of a simple application. These kinds of little tiny ports can almost certainly be done with some automated tools. Almost always the case that you'll be doing these ports are you've got a vertex shader that you've had around, you've been banging up against the limit of the number of bone matrices you want. You're going to probably want to jump the vertex shader first up to the pound version 300, and so you're going to have the pound version 100 shader, fragment shader be ported up as well. Is everyone clear on that? Very minor stuff. The ES goal of not giving you multiple ways of doing the same thing. So you lose varying, but you get in and out, which is functionally clear. And then let me very briefly talk about a half-a-day conservation effort that will possibly end up saving you some time. Pound version 300 ES precision high-P float. Sampler to the float map. So we've got these higher precision textures out there now. But by default, the old samplers would be a low-P sampler. So you would be possibly, on some implementations, scratching your head for half a day trying to figure out, why do I have these gorgeous FP16 textures, and I'm trying to pull them in, and they're coming in and they're getting truncated down to very low precision stuff. What is going on in this? So think about that. You're going to want to declare on the right-hand side what the sampler precision is. And in this case, I decided to go up to high-P sampler 2D float map. The new samplers do not have a default precision. So the other one that will end up scratching your head for a while. Just like in the shader as a whole, you have to declare the overall precision of your float in the fragment shaders. For both vertex and fragment shaders, you have to declare the default precisions for each one of your samplers, or declare them individually sampler by sampler. So precision low-P sampler 3D Q map. So effectively what you've got going on right now is you've got a phenomenally more rich shading environment for you to be going in. A lot of the things and the limitations that used to be there that you had to worry about, you don't have to worry about it anymore. You're going to be thinking about what your budget is for getting your work done, and you're going to go off and do it. And I think you're going to enjoy this new healthy environment a lot. Thank you very much.
All right, so I will talk about the texture compression formats in OpenGL ES 3.0 and also OpenGL 4.3. So if you only want to remember one slide, you should look at this slide and take a photo of it. Basically, we have new codecs that provide higher quality. They provide alpha, 1-bit and full alpha. And they also enable 2 and 1 channel texture, R and RG textures. And they are mandatory in OpenGL ES 3.0 and OpenGL 4.3. So finally, there is a mandatory texture compression system, so developers don't have to check for it. So why do we need texture compression to start with? Well, this is a simplified version of a rendering system. You have the memory and then you have the GPU. And you have 2 problems. The memory can get full, and secondly, the bus can get congested, and then you will lose performance. So if you compress your textures, you will fit more textures into memory. There will be less traffic on the bus, and that means higher performance or lower power consumption, or both. And it's also cheaper to transmit textures over networks, which is of course nice. So history first. ETC1 was standardized in OpenGL ES, and it's now supported in Android from Froyo and above, which means there's a lot of handsets out there that supports this. The problem, however, it was never mandated as mandatory in OpenGL ES 2.0, so developers would have to check if it was there. Also, it lacked alpha support and support for RG textures. So ETC2 is an updated version of ETC1. It has the same bit rate as ETC1, but enhanced quality. It's about 1 dB better than ETC1, and also 0.8 dB better than S2TC, DXTC, and 1.6 dB better than PVRTC, approximately. And what does that mean? Well, I'll show you some pictures, because that is nicer. In the top row here, you see a texture that works pretty well with ETC1. The nice thing is, it will never be, ETC2 will never be worse than ETC1, it will always be as good or better. But on the 2 lower rows, you see artifacts, especially here in the edge between 2 different chrominances, and you can see that right here. That looks bad, and that will be much better in ETC2. The second improvement is when you have smooth transitions between things. For instance, here you have a smooth transition between green and yellow, and that is better preserved in ETC2. And also, for instance, here you can see blocky artifacts and ring artifacts, but in ETC2 it looks better. And also for light maps, you will have improved quality. So that's for the quality improvement. Now about the backwards compatibility. So ETC2 is backwards compatible with EC1. What does that mean? Well, if you have an old EC1 texture, you could load it as an EC2 texture, and the hardware will decode it just correctly. And this means that if you are developing content, and if you create an ETC1 texture, it will be able to run on all OpenGL ES 3.0 devices, all OpenGL 4.3 devices, and all of the 370 million or so Android devices that can handle EC1. Another thing is that ETC2 and EC1, they typically share a lot of the blocks. So for instance, you see here to the left, you have an ETC1 texture, and of course all the blocks here are ETC1. But here you have an ETC2 texture, and many of the blocks are ETC1 blocks, and just some of them are ETC2 blocks, or that improved. So you could store these in the same file. You could store both all the ETC1 blocks and then the extra ETC2 blocks. And then, hence you could basically get two, in the same file, you could support both old devices and new ones. And it's not going to cost you 2x of the reliability. So, flavors of ETC2. ETC1 could only handle RGB textures, but ETC2 comes in several flavors. In the first row here, we have the normal one, RGB. And the second row is RGB8. This is full alpha support, 8 bits per pixel. But we also have a punch-through mode where alpha could be either completely transparent or opaque, and that's a 4 bit per pixel format. All of these formats also exist in RGB and sRGB. Going on to EAC, ETC1 could only handle RGB textures, whereas two-channel textures are typically needed for normal maps. So EAC gives high-quality one-channel and two-channel textures, so you could be able to support things like that. You also have two flavors of it. You have the unsigned and the signed. And the difference between them is that the signed version can preserve 0 exactly, just in the way that as Benj was talking about with the specification. There's a compressor. You could download it today from devtools.ericsson.com/etc. It compresses all the new formats plus the old one, ETC1. It has two modes, fast and slow. And the slow mode is faster than the previous compressor, but also gives higher quality. And it does exhaustive compression, so you will not be able to do any better, which is nice. The fast compression will give you good compression efficiency and also reasonably fast. It's possible to do even quicker compression than the code that we have here. For instance, we have internally implemented compression with speed equivalent of HD in 30 frames per second on a quad-core 1.4 gigahertz ARM. So basically, there shouldn't be a problem compressing in real time also. When you want to transfer these images over the network, ETC2 is 4 bits per pixel, so typically sending a JPEG would give you equal quality with a fewer number of bits. However, you could pack ETC2 textures using zip or LZA, and you could get more efficient transmission. And there is recent research that shows that if you use a special purpose packer, you could actually pack ETC files to smaller than JPEG for equal quality for JPEG. So at around 2.2 bit per pixel. So that's basically what I was about to say today. So in summary, we have new codecs. They provide higher quality, alpha, 1 bit and full alpha, R and RG textures, and they are mandatory. So developers do not have to test for them. And there's a compressor available in black. So thanks.
A couple of comments. I'd like to say, Jacob's being modest, he is the inventor of ETC2, certainly at least the lead on the research. And Ericsson has shown amazing public spiritedness and done amazing things for the industry by making this intellectual property available to us without royalty. So that's really terrific. For conformant implementations. So I have a few more words to say, and then we're going to have our Jack in the Box series. We have about 7 people who are going to make 90-second or hopefully 1-minute presentations with a single slide, and I will be right here brutally suppressing anybody that goes over time. I need you here and ready to go. We're going to go in alphabetical order. You guys know who you are. Get on up here. I just wanted to, I made these slides for the press, right? They don't deal with lists of features and they don't know what the features mean. But just to show some of the kinds of things that I've seen demo teams putting together. Some of the features that we've got in the capability. This is a demo that our demo team is doing. They're British, it rains a lot. So they like heat and they like bright light. In this demo, among other features, they render to a 10-bit render target and then tone map it in order to get that nice glare. They use the shadow samplers in order to have the various parts of the vehicle shadow themselves. Unrelated to that, they use multi-layer textures so that as this vehicle drives over the ground, it can damage the dust and reveal other stuff underneath it, and have damage maps and things like that. So that's kind of cool. And then this is something Laszlo's going to talk about, the Kishanti Geo Benchmark 3. This is a fully deferred rendering engine using a G buffer with the with the MIT technology. It uses occlusion queries in order to know when it should do lens flare. Everybody likes to do that. It uses instance drawing for both the vehicles and these shaped particles that you see coming up. And I think he's going to show us a video when his turn comes. I have one more slide. Where are my other speakers? I need you. Ready to go. So one other thing, not related to ES3. Okay, we're done with ES3. This is just what's happening today. We have been working much more closely with the ARG in the last couple of years than we used to. And one of the things we've decided to do is it makes sense to share extensions a lot. So we've introduced a new tag. You're familiar with ARG and OES. Now there's a third tag, KHR. These are Khronos extensions. It means they're ratified by the promoters and covered by the IP agreement. They're as official as they can be, but they're defined against both APIs. And we've introduced 2 on Monday as part of the big release party for various specs. One is KHR debug. It's an extension of ARG debug output. I don't know if Christoph is here, but anyway, brilliant job on that. So this will, it's optional. You won't have it in all implementations, but it can give you a significant leg up on debugging applications. A second one, ETC2 is fantastic, the best compression system we've ever had. Recently, as a research project, we've come up with something else, which is fairly radical and different. It's a compression scheme that supports a very wide range of bit rates. So you can turn the knob to say exactly how much quality do I need, how much bit rate can I afford for this texture. And it's extremely flexible. So any bit rate, any number of components, well, as I said, and quality, again, that exceeds S3TC and PBRTC at comparable bit rates, and it's quite extraordinary. All right, well, I'm going to do my slide because it's here. I've been working on this for 5 years. I'm incredibly excited about this. On Monday, we announced that our mid card GPUs are all designed to support this, and as soon as there is a conformance test, we'll prove it. We have an emulator on the website. By the way, Qualcomm has an emulator. There's lots of stuff out there for people who are interested in ES3. And then on ASTC, I'm proud to say that it was developed primarily as a research project for us. We did have some very valuable input from AMD on the technical side, and there is some intellectual property of theirs. We, again, have done, inspired by Ericsson's example, said we want to see this in the standard, so we're not going to charge royalties for this. For conformant implementations. And we announced hardware on Monday that will support it. Patrick, so 90 seconds.
Okay, so Peter from DMP, basically 3 things that I would like to highlight. People who don't know the DMP, it's one of the graphics IP vendors in the mobile space. We have been following the Khronos OpenGL ES standard roadmap for pretty much from the beginning. So starting from the ES1, ES2, and now ES3. So I said 3 things. The first thing I would like to highlight, hopefully it's a positive news to many of you. So we actually have been quite dominant in the camera OEM space nowadays. So if you look at the top 7 global camera OEM manufacturers, so 5 of those are already licensing graphics IP, which means that there is already some cameras, but will be huge amount of camera devices that will support Khronos-based OpenGL ES standard. It can be used for UI purposes, but also together with the OpenGL will be used obviously for different type of image processing functions. Then the second thing is that our main product family called SMAP-S is also supporting now the latest OpenGL ES3 standard that was announced on this Monday together with the Khronos announcement. And the final thing is that please come visit tomorrow our expo. You will hear and see more about our stuff there. Thanks.
Thanks, Petri. We'll talk about what it means to support later. Actually, to say support, you have to pass the conformance test. So we need a little asterisk there. Okay, next.
Hi, my name is Ian Romanek. I'm at Intel's Open Source Technology Center. We are developing a fully open source ES3 driver. A very pre-alpha version of it is available as of about 2 hours ago. There's a bunch of holes in it. We don't support ETC2 yet, for example. And there's a few other things. We're targeting to have full support with conformance, assuming it's ready, by Q1 of 2013, so probably February timeframe. So it'll be our Valentine's Day present to everyone of us.
Thanks, Ian. I did neglect to say the roadmap for conformance. We are hoping to begin accepting conformance submissions before the end of the year. That's the plan. Some of us don't believe it, but many of us do.
My name is László Kisonki. We develop the GL benchmark software benchmarks. OpenGL benchmarks, and obviously this demo was done on preliminary implementations, but we were trying to use the latest features. Many were already mentioned by Tom, but I'm just listing that. We have multi-render targets, obviously, with floating point textures, depth maps. We have 3D textures for particles, animations, instancing, array textures, and also occlusion queries. So basically all the major new features are implemented in this demo. Thank you.
And Laszlo wins the prize for best early ES3 eye candy.
I'm Rauli. I've been working on our benchmarks for ES3, and it contains 2 scenes. One racing scene, which is its screenshot, and second one is a character-based sequence, which is featured in this one. We are also using occlusion queries, multiple render targets, render target anti-aliasing, and most of those new features that are introduced in ES3 in this benchmark. And you can expect it to be out in a month or 2. Yeah.
Hey, hang on a second. I forgot something. Patrick Kazi is reminding me, he very kindly, he and his co-author, kindly donated a couple copies of OpenGL Insights. I have 2 trivia questions. I'm going to steal this idea from the yard. And so I'd like to give away 2 of the books, and can we give away the others during the GL doc? These are OpenGL trivia questions. If you are in the working group, you are not allowed. So the first one is, we heard about ETC2 and ETC1. What is the required compressed texture format in OpenGL ES 1.0? Okay, sorry. Good guess. Formally speaking, you can't call compressed text image 2D, but there is a compression format. What is it? I'm going to take none. I was thinking of paletted compressed textures, which are a required feature in ES 1.1, which nobody ever liked, so it's gone. Okay, I can see that my taste in trivia is a little arcane. So that gentleman there, if you'd come up later and meet our author and get your cut. This, by the way, this is a brilliant book. It's beautiful and has fantastic stuff in it. Okay, second trivia question. What capability is added to OpenGL ES 2.0 by the extension OES texture in pot? Who said first? See, this was a trick question. Who's next? It's a horrible name for the extension, that's a hint. There were a couple people, who thinks they were first? The guy in the green shirt down in front, is that you? Okay.
Yes, was non-power too.
Okay. I'm doing really badly at this. Barco's going to kill me.
Tom, I don't even know the answer.
Bill?
I wrote the extension.
What capability is added to ES2 by OES texture MPOT? You don't know? Sorry? That's close enough. It's the ability to do full wrap modes and all the filtering and the mapping, I believe, as well. So yeah, give that man a book. Sorry. Next time I'll practice.